Hi, and welcome back. So in this video, we're going to continue our study of neural networks, but have a special emphasis on techniques you can apply in order to avoid overfitting when training neural networks. Okay, so when we want to avoid overfitting, and overfitting is something we discussed in previous videos, so please go back and watch them if you've forgotten. But the basic issue in overfitting is that it looks like the model that we're training is performing really well on the training data, but actually if you ran it on new data, it performed poorly. So the gap between the in-sample error and out-of-sample error is large. In particular, you minimize the in-sample error in some sense too much. You overfit it to the training data, while the out-of-sample error is pretty poor. So there's several techniques known, in particular for neural nets, in how to avoid this. So two of the techniques are basically some techniques that we've seen before. I'll try to discuss them in this context, validation, and then the new one is early stubbing. So that's a technique to use together with validation. So let me try to explain what that is. The second technique that we'll use is regularization, which is also something that we've seen before, and I'll just in this video describe how to use regularization together with neural nets. Okay. Finally, a very popular technique for avoiding overfitting is the one called dropout, but we'll not be talking about this one in this video here. Okay, so validation and early stopping. So the basic idea here is, like we talked about in previous videos, we want to use a validation data set in order to make decisions on which model to use. So what you see here on the plot below is the training of a neural net. And you can see here the red one is the training loss. So we've been training a neural net for regression on the Boston housing data set. And the basic idea is that we want to predict the price of a house with least squared loss. And what we've been training is a neural net with one hidden layer using Relo activation. So if we watch this plot, so what's going on here? So the red one is the training loss. As you can see, it steadily decreases. And then, even though it zigzags a bit, it generally decreases until some point here maybe around these 10,000 epochs. It's performing very well on the training data. But if we at the same time have set aside a small data set for validation, so we took aside 20% of the data that was not used for training, then what you can see here is that, in fact, on this validation set that's not used for training, the performance actually get worse after a while, right? So it starts by decreasing the loss, but then it actually increases. So in some sense, we're overfitting around this place here. And indeed, if we actually look at the model that we train here at the end, so if we look at just the one that has the best training error along all these epochs here, so just all the best set of parameters that we ever saw with respect to the training loss, then what we end up with is that the neural net that we get, if we just use the best one that we've seen with respect to training loss, ends up with an least squared loss on new data. So we set aside some test data that we've used to measure. Of course, this is not the same as the out-of-sample error, but it is a test error. And actually, the one that we get has something like 17.4 in loss. And we can compare that to one where we use validation. So if we use validation and we stopped with the set of parameters that looks best with validation, then we end up with something better, namely 17.07 in loss, right? So you can use this validation set to avoid overfitting. So let's just try to visualize what we have here, right? So we ran 10,000 epochs of stochastic gradient descent. And the best in-sample error that we saw, so the red one here, was 6.2, right? So somewhere around here, 6.2 in loss, as you can see here on the y-axis. And yet the out-of-sample error, which I guess we approximate by a test error, so we have a test data set that we set aside, is something like 17.4. Okay, so, so there's quite a large gap. Whereas on the other hand, if we use a validation data set, the blue validation scores that we have here, so after every epoch, we computed the loss on the validation data set, and we saw the one that got the best validation error. It's somewhat larger, right? But that makes then the in-sample error, which makes sense, right? Because we are actually training, we're training on a data set that we're not measuring on, right? So in the validation set, we're training on the training data set, measuring on the validation set. So the best that we see here is around 12.5. It's the one that we see up here to the left. And here you can see that the in-sample error at this model that we've trained at this point is something like 8.5, 8.5. So it's worse than the best red one that we've seen. Yet the out-of-sample error, which we approximate by a test error on a test data set that we set aside, is actually better. It's 17.1, right? So here again, this is an example of where we can use validation when we do this whole training. It's not necessarily the model that looks best on the training data that's actually the best choice of parameters. But using a validation set, which is something that we don't train on, we only compare the models that we see the performance on the validation set. This actually gives a better performance. Okay, so using a validation set, we actually choose the model that we had after this epoch down here, even less than 1,000 epochs, rather than these models that we have out here that perform a little bit worse on the test data set. Okay, so basically the idea is, right, as we also said before, set aside some 20% of the training data if you can afford it as a validation set dval. After every epoch, compute the loss on the validation set, and if the validation loss is smaller than the best validation loss we've seen so far, then we store the current model parameters and keep them as the best seen so far. And once we're done with all the epochs, we use the one that had the best validation score. That's the model that we keep. Right? So this is what we did in the previous figure. Now, early stopping is a technique to add to this if you want. And the basic idea in early stopping is that as we train and keep going, if at some point we haven't seen any improvement to the best validation score for at least some k epochs, maybe you hard code k to be 100, 10, depending on how slow it is to run an epoch. Then if you haven't seen an improvement for a while, then you just stop training and use the best parameters seen so far, right? So it's a way to cap the training time. So maybe if we go back to this figure here, as you can see, right, once we've reached this stage of training, we found a model and it doesn't improve for a long time. None of the succeeding epochs improves it, and actually we wouldn't have stopped before, right? Because here every epoch improves the validation score. So that's the basic idea in early stopping. You just kind of give a parameter k and say, well, if I've seen k epochs without any improvements, then I just stop and use the best parameters I've seen. Right. Good. The second technique that we mentioned that we could also use together with neural nets is weight decay. So in the previous video, we used weight decay together with linear regression also to combat overfitting. And if we use weight decay with linear regression, this is what was known as rich regression. So the basic idea here is that we had the least squared loss that we know from linear regression, and we added this weight decay term, which is a hyperparameter lambda times the sum of squared weights. Right. So this here is the normal linear regression loss, and this is the weight decay parameter, which means that the model that we come up with, the hyperplane represented by W, this W that we use, will prefer small weights. Right. And you can do a similar thing for neural nets, and it actually seems to work well in practice to avoid overfitting. So for neural nets, right, we can say for any loss function L that we care about, it could be cross entropy loss like in the previous video. We have the in-sample error. This is the standard part of the in-sample error. You average over all your training examples, apply the loss function to the prediction made by the neural net on xi and the label y. And then we add in this weight decay parameter or term. So sum over all the weights in the neural net. So that's what this is supposed to be, right? So the neural net has all these weight matrices. Just sum over all the weights and square them. So very similar to in linear regression. And maybe one thing that's important here is that you typically do not include the biases when you add weight decay. Okay, so that's just a thing to remember. You only sum over the weight matrices, not the bias vectors. Okay. And right, so if you're doing gradient descent to train one of these neural nets, as we saw in some of the previous videos, right, we use backpropagation as the algorithm for computing gradients, right? So we have this new in-sample error. This is not the same as we had before, right? We added the weight decay parameter. And before, right, we construct the entire computation graph computing this loss, because that's the one that we need to compute gradients of with respect to all the weight parameters. What we have to do here is that we have to remember to include this weight decay parameter in the computation graph for backpropagation, right? Because it's part of the loss that we're minimizing. So this has to be part of the computation graph. That's all that's required. And maybe one thing to be aware of, like, so here we have a sum. And in some sense, this means that these weight parameters, they both occur in this part of the computation graph, and they also occur in this part of the computation graph. And maybe one thing, since if you remember it, also gradients are additive. If you have a sum, they're additive. So you should just kind of sum up the contribution from over here and from the weight decay term. You can also, if you remember the computation graph when we talked about it, if nodes were branching, so some parameters sent to multiple places in the computation graph, then a backpropagation will compute partial derivatives on all these edges that go out of this node C. And then we had the special rule that if we had multiple outgoing edges, the actual partial derivative, you had to add up all these partial derivatives you computed on the edges, which basically means that we can just, in some sense, compute the gradients that we did before for this first part of the loss function, the one that we already know how to deal with. And then we should just add the contribution from the weight decay terms to all the partial derivatives. And the nice thing here is that this is the sum of squares of all the weights in the network. And this means that, well, the partial derivatives, if I have one of the weight parameters, one of the weights in the network, since this is additive, right? Yeah, the only thing we have to do is to, if you take the partial derivative with respect to W, the only term that remains is 2 lambda W. So which just means that for every weight parameter, once we've done back propagation, actually on the first part of the loss here, all we have to do is really add 2 times lambda times the current value of W to the partial derivative with respect to W. So it's a very simple update, right? You just add a little bit to all these gradients relative to what the values were before. Of course, if you use automated libraries for computing gradients, you can always just, you just have to evaluate this whole loss functions, for instance, using PyTorch, and then it will know how to compute the gradients for us. Okay, so maybe here's just one final plot for when you use regularization. So it's the same data set as before. We have to predict house prices, and we have set aside a validation data set. And as we did before with regularization in previous videos, when we have this hyperparameter that we have to choose, I guess it's called lambda here in the plot, it's just called C, just for simplicity in the plotting code. So then what we have to do is, right, we can run, we can train a neural net with different values of this hyperparameter lambda, the penalty on the weight decay term. And what we can see here is that we get different performances, right? For instance, if we have no regularization, we basically get a plot that looks at the blue one here. The validation score doesn't get that great. We can see here that actually if we use a validation loss, the penalty on the validation term is 0.1, we actually get a really good performance down here on the validation data set, which we use this regularization parameter. So it seems at least what we'll do now is we'll compare all these models with all these different hyperparameters and choose the best one, which means the setting of 0.1, right? And wait, so one thing to remember here, which is really important actually, when you do regularization together with validation, is that when you're training the neural net, right, we're training to minimize the in-sample error plus the weight decay term. So that's important. When you're doing your gradient descent, you have to include the weight decay term in the loss. But for validation, we're only interested in which model is the best, right? Which one makes the best predictions. So here, of course, right, the important thing is that it's the raw loss. There's no weight decay here, because when we're comparing them, right, we really just want the one that performs the best on the validation set, because the validation error is a proxy of the outer sample error. And for the outer sample error, we don't care about the regularization term. We just want as small an outer sample error as possible. So the really important thing is here, when we make this plot, we train each of these models with their regularization term, like with the weight decay term. But when we plot these validation losses, we actually plot the raw loss, the raw in-sample error without the weight decay term. And that's crucially important to remember. Okay, otherwise you'll probably always get that the one using a weight decay parameter of 0 is the best one, because, well, it just minimizes the in-sample error directly. But anyways, this is the basic setup, right? Okay, so all the others here, right, you have an additive term, a non-negative additive term in the loss function. So it'll just get worse with higher regularization parameter. Okay, so just remember that. Don't include the weight decay term when you're plotting the validation errors or measuring the validation errors. Okay, so that's what we wanted to cover for how to avoid overfitting in neural nets, some of the basic techniques.